Hi everyone, in this problem I would like to talk about an application of parametric equations. A rocket is launched from the ground with initial velocity of 100 meters per second at an angle of 40 degrees. Find the parametric equations to model this motion. Graph the parametric equations. The assumption that I'm making is that g equals negative 9.8 meters per second. Notice that my acceleration due to gravity is in meters per second squared, and that matches the units of my problem, which is also in meters and seconds. If you have a different problem that is in feet or millimeters or minutes, you will need to convert your units or use a different acceleration due to gravity. To model the horizontal component, I have x of t equals v naught times cosine of theta times t. In our problem, that equals 100 times cosine of 40 degrees t. To model the vertical component, I have v naught times sine of theta t plus 1/2 times the acceleration due to gravity times t squared. In our problem, that will be 100 sine of 40t minus 1/2 times 9.8 t squared. To plot this, notice that I'm not plotting x as a function of time and y as a function of time. I'm not creating two different curves. I am plotting a parametric curve, and in the x component, I have the function for x. So instead of plotting a point like over 3 up 5, my first component in the x component, it is a function of time, a function of my parameter t. And then over here in the y position, the second coordinate, I have my function for y. Now, if you have a graphing utility or you're working in Desmos or something that needs radians, you can convert to radians. Remember, I'm in degrees, but you could convert to radians by multiplying 40 degrees times pi over 180. All right, let's take a look at this in Desmos. So if you type this in Desmos, I'll just scoot back to the beginning of my line. I have big parentheses and a comma, and then the closing parentheses. So I'm literally plotting x, y points. So everything before the comma is my x component. And so x, as we said, is 100 times cosine of 40 times pi over 180, and I put the t right in front there so it didn't get confusing with the comma. Then for the y component, again, I have t times 100 times sine of 40 times pi over 180 minus 1/2 times the acceleration due to gravity t squared. And we need to set some bounds for my parameter t. Let's go t equals 0 all the way up to 15. And now I'm going to add on another piece. I'm going to add on a slider bar. And I've done that here in Desmos. You don't have to do that. But what that allows you to do is it allows you to set the value for A, which is time. And you're going to start that value. When I click play, notice that as that time changes, I can see what's happening to the motion of my rocket. And that makes sense, right? When the rocket is starting, when time is 0, when A is 0, my little parameter for time here, when that's 0, the rocket is at the ground. And then it launches and up in the air it goes to a maximum height. Notice that the horizontal axis is the distance, the horizontal distance, and this vertical axis is the vertical distance. Time, where is time? Time is over here, it's my little parameter. So according to this model, the maximum height of approximately 200 and something is achieved when time is 6.5. And then the rocket will keep going, fall back down to Earth, and it reached a maximum horizontal distance of about 1,000 meters, and it fell back to Earth at 13.02 approximately. If we want those exact values, we can certainly solve for them analytically. But your graph for projectile motion should look something like this. It should look like the path that your dart or rocket flew up in the air and fell back down to Earth.